educational videos by mmsprogramcivil.com. Please visit website mmsprogramcivil.com for all the videos. Chapter 11 and Chapter 12, Design of Compression Member, Short Columns. Classification of columns based on their reinforcement orientation. So, these are tied columns, these are ties, where the main longitudinal bars of the tied are tied with lateral ties. They are tied columns. This is spiral columns. The main longitudinal bars are tied with spiral reinforcement. You can see these are spiral reinforcements. Classification of column based on type of loading. Column under pure compression, where you have an axial load passing through the CG. Column with uniaxial loading, where you have one axial load and a moment, okay, which can be represented in this manner also, that your axial force will be acting at an eccentricity Ex. Ex is equal to mx by p, and Ey is 0 because this is uniaxial column. Column with biaxial loading, you have one axial load and two moments, that is mx and my, and you can represent this in this manner, that axial force at a eccentricity Ex and Ey. The loading on the column can be purely axial under pure compression. Eccentric with respect to one axis, carries axial load and moment in one direction, called as uniaxial column, or eccentric to both the axis, carries axial load and moment about both major and minor axis, and it is called as biaxial column. In practical field, usually all the columns are biaxial columns, as code suggests, considering minimum eccentricity in both the directions. Okay. Classification of columns based on slenderness ratio. Okay. As according to IS 456 2000, a compression member is classified as short column and slender column. Definition of unsupported length. Unsupported length is that taken as the clear distance between the floor and the shallower beam framing into the column in each direction at the next higher floor. Okay. So say this is your x-axis, this is your y-axis. Along this axis, this is the shallower beam. Okay. Then the clear distance from the bottom of the beam to the top of the lower floor is your unsupported length Lx. Similarly, along this direction, this is the shallower beam. So the distance, clear distance from the bottom of the beam to the top of the lower floor will be Ly, that is unsupported length Ly. Okay, that is about y-axis, right? So Lx and Ly are unsupported lengths with respect to x and y-axis, right? Over here you have to consider your RCC phase, okay, and not the plaster phase. And over here you have to consider the slab phase and not the flooring top phase, okay. Effective length Le is equal to K into unsupported length L, where K depends upon the end resistance of the column. When the ratio of effective length Lex by dx about major axis is less than 12 and Ley by dy is less than 12 about minor axis, then the column is designed as a short column. Okay. When the ratio of effective length Lex by dx about major axis is greater than equal to 12, and Ley by dy is greater than equal to 12 about minor axis, then the column is designed as a slender column. In the figure shown above, Lx and Ly are the unsupported length about x and y-axis, right? In this figure, you can see the beam depth is the same, okay? When we consider this column, then this is your Lx and this is your Ly, okay? This is from the floor, that is bare floor of the slab, right? And this is from the RCC face of the column, right? Bottom face of the, sorry, bottom face of the beam. Okay, fine. So this figure shows and gives information regarding the type of failure. Okay, over here the line OA specifies that the short column undergoes a material failure, and OB shows that a slender column goes under a material failure, and OC shows that a very slender column goes under buckling failure, right? So buckling failures are not allowed. Okay, material failures are those failures in which the failure occurs due to concrete and steel reaching its yield stress and strain, right? In case of buckling failure, the material does not reach its yield strain and stress, so that will be uneconomical, and also the failure will be very sudden. Okay, so buckling failures are not allowed. Okay, the short column fails under axial loads without undergoing any lateral deformation. The collapse of column is due to the material failure as both concrete and steel reaches its yield stress value at the failure, right? So this is a compression failure, right? This is a compression failure where you can see that the material gets reaches its yield stress and the failure occurs. Okay, short and slender column subjected to direct load Pu and moment Mu and gets collapsed due to material failure as concrete and steel both reaches its yield stress value of the failure. Okay, this is a compression member. If it is in a uniaxial or biaxial compression member, then also the failure will be somewhat like this, and it will occur due to the failure of concrete and steel, right, as they reach its yield stresses, right. A very slender column can become unstable even under small axial load and collapse due to elastic buckling before the concrete and steel reaches their yield stress value for failure. So this is your buckling failure. Okay, this such failures occur even under small loads, where and at the time of the failure, concrete and steel do not reach their yield stress, right? And so this are very dangerous type of column, right? So such columns are not allowed. Design of such columns are not allowed, right? The third case is not acceptable, hence IS 456-2000 restricts the slenderness ratio given as below. So for this reason, the code has restricted the limit of slenderness ratio. Unsupported length by least lateral dimension should be less than equal to 60 in case of braced column, and unsupported length divided by least lateral dimension should be less than equal to 30 for unbraced columns. Okay, so for this reason, to avoid buckling, this limit has been suggested by the code. Fine. This is a column with one end free. Furthermore, in case of one end of column free in any given plane, the code as according to clause 25.3.2 specifies that unsupported length L should be less than equal to 100 d square by d, where d is the depth of the cross section measured in plane of the cantilever and b is the width. Okay, so these are some standard conditions given in the code. Code recommendation for idealized boundary conditions. First, column braced against side sway. First case, right? Both ends fixed rotationally. Okay, so both ends are fixed. In that case, your effective length will be equal to 0.5 times the unsupported length L. Okay, both ends free rotationally. It is free in rotation. In this case, your effective length is to be taken as equal to unsupported length, right? So these are standard values given in the code, but recommended is 0.65 over here, and over here it is 1, right? And one end fixed and other pinned. Okay, one end fixed and other pinned. Okay, in that case, the standard value is if effective length is equal to 0.7 times the unsupported length. That is standard, and recommended is 0.8. Okay, so these are some standard cases for braced columns, right? Similarly, some standard cases for unbraced column are also given in the code. Okay, column braced against side sway, right? Effectively held in position and restrained against rotation at one end, that is this end, and the other end restrained against rotation but not held in position, that is this end. In this case, recommended is 1L and theoretical value is 1L and recommended is 1.2L, right? Effectively held in position and restrained against rotation in one end over here, and other end partially restrained against rotation and not held in position. So this is the case over here. Recommended value is 1.5 times the L. Okay, L is unsupported length. Effectively held in position at one end but not restrained against rotation, that is this, and the other end restrained against rotation but not held in position, that is this. In this case, standard value is 2L and recommended is also 2L, right? Okay, so these are some standard cases given in the code, but actually in practical fields such standard cases usually do not occur. Our frame joint is a partially fixed, is in a partial fixed condition, right? So for this, code has given some uh, data through which you can find your value of k. Okay, in absence of more exact analysis, the effective length of the column in frame structure may be obtained from the ratio of effective length to unsupported length, that is LA by L, given in figure 26. This is figure 26 given in the code, when relative displacement of the end in a column is prevented. So this figure can be used for column with no sway. Okay, and figure 27, when relative displacement of the end is not prevented. Okay, so this figure can be used for finding k for column with sway, right? Okay, in the later case, that is in this case, it is recommended that the effective length L ratio, and that is L by L, should not be taken less than 1.2. Okay, this is very important. Okay, so a description of this figure a little bit. Okay, figure 26, effective length ratio k is equal to L by L for a column in a frame with no sway. The value of k varies from 0 to 1. That means the effective length of a column will be always less than or equal to unsupported length. This is very important. If your column is with no sway, the value of k will vary between 0 to 1. Okay, and your effective length will always be less than or equal to unsupported length. So when the conditions are fixed, okay, the value is 0.5. You can see this figure and see this figure where it is, the value of k is 0.5. So we can see when it is fixed, it is 0.5. Okay, when it is hinged and fixed, the value is 0.7. Okay, so you can see where it is fixed and hinged, then it is 0.7. When it is hinged and hinged, it is 1. So when it is hinged and hinged, value is 1, right? So this standard cases have been already taken in this graph, right? Okay, now let us see a little bit of figure 27. Figure 27, effective length ratio k is equal to L by L for a column in a frame without restraint against sway, right? So the column is, it's a sway column, right? The value of k varies from 1 to infinity. That means the effective length of a column will always be greater than the unsupported length, right? Value of k varies from 1 to infinity. Okay, fine. So now a question comes in our mind, that how to decide that whether the column in a story is a sway column or a no sway column, right? So code is given in a very easy method, that is stability index q of a story, right? An approximate way of deciding whether a story column is a sway column or a non-sway column is given in IS 456 2000, right? When the stability index q is less than equal to 0.04, the column is designed as non-sway column. When the stability index q is greater than 0.04, then the column is designed as a sway column. Okay, so with the help of stability index Q, you can decide whether you will design the column as a sway column or a non-sway column. Okay, so Qi is equal to sigma pu into delta u divided by capital Hu into small hs, right? So Qii. Okay, so you have to find stability index Q in both the direction, that's x and y. So Qix and Qiy. Okay, I represents the story number, right? So there can be many number of story in a frame. So I represents the story number, and x represents the axis, and y represents the y-axis, right? Okay, fine. So now say this is your x-axis and this is y-axis. So first we'll try to understand to find Q in this direction. Okay, so this red frame is the original frame, and the blue frame is the frame after sway. Okay, that when the load is applied, we can see that this point has shifted to over here. So in this direction, this is delta 1. Okay, and over here this is delta 2, right? This we are considering this story, right? Okay, we are considering this story. So delta u will be delta minus delta 2. Okay, that is your delta u. Okay, and pu is the summation of all the actual load in the of the column in the story, right? So here pu will be p1 plus p2 plus p3 plus p4, right? All columns in the story. Okay, HU is the lateral force acting, total lateral force acting in the story in this direction. HS is the height of the story, right? So this is how you can find QIX. Similarly, you can find QIY. Simple. For finding QIY, your delta U will be delta 3 minus delta 4, okay? And PU, sigma PU will remain the same, okay? And HU is the total lateral force acting in the story in this direction, right? And HS is the story height. So this is how you can find stability index Q and decide whether the column is a sway column or a non-sway column. Okay, fine. Now minimum eccentricity for the short column, right? Now code suggests that you have to at least consider minimum eccentricity about major and minor axis, though there are no moments. Okay, fine. So this is an column under pure compression. Okay, then you have only one axial load that is passing through the CG, right? As per clause 25.4, all the columns shall be designed for minimum eccentricity as formulated below. You have to find ex minimum, ex minimum. Ex is this and ey is this, right? Okay, so ex minimum can be found by this formula given in the code: unsupported length Lx by 500 plus b by 30. This is b, right? Ey minimum can be found by this formula: unsupported length, that is Ly by 500 plus d by 30. This is d, right? Fine. Okay, but code also says, but in no case ex minimum and ey minimum should be less than 20 mm. If it is less than, it is found to be less than 20 mm, then you have to at least take 20 mm, right? Okay, when ex minimum is less than 0.05 b. Okay, so this is 0.05 b. This is your b. Okay, and this is your 0.05 b, and your ey minimum is less than 0.05 d. So this is 0.05 d. Okay, this is d. Then only you can design the column as pure axial loaded column. Okay, say suppose e minimum is less than 0.05 b and ey minimum is greater than 0.05 d, then you will have to design this as a uniaxial column. Say suppose your ex minimum is greater than 0.05 b and ey minimum is also greater than 0.05 d, then you will have to design it as a biaxial column, right? So for designing it as a pure axial loaded column, this condition has to be satisfied. Okay, similarly, column with axial load and uniaxial moment. As per clause 25.4, all the columns shall be designed for minimum eccentricity as formulated below. Here we have one axial load and a moment which is at a distance ey. Okay, eccentricity is ey. Okay, fine. So first you have to find the eccentricity ey due to the design moment my by p. Second, you find e minimum. by this formula. Take the larger of these two, and that should be greater than 20, right? Greater than or equal to 20, right? Otherwise, if it is not, then you will have to take EY as 20 mm, right? In other direction over here, we don't have any moment. So consider the larger, okay, over here, we will find EX minimum, right? Because there is no eccentricity in actual design load. Okay, so still we will have to find Ex minimum. Ex minimum can be found by this formula: unsupported length Lx by 500 plus B by 30. If this is found to be less than 20 mm, then you have to at least take 20 mm, right? Fine. Now, see, suppose this eccentricity Ex is found to be greater than 0.05 B, then this column has to be designed as a biaxial column. But say suppose this is found to be less than 0.05 B, then this can be designed as a uniaxial column. Okay. Similarly, column with axial load and biaxial moment. Okay. Say this is your EY, this is your EX. Okay. So find EY due to design moment MY by P. Find EY minimum. Take the larger one, should be less than equal to 20, right? Should be greater than equal to 20. Okay, otherwise you will have to at least take 20. Okay. uh, Over here, again find Ex due to design moment Mx by P. Find Ex minimum. Okay, take the larger of these two, and that should be found to be greater than 20, otherwise you will have to at least take 20, right? So this is how we check whether column is an under pure compression or uniaxial or biaxial column. Okay, one another important point. Say if your Ex minimum is found to be greater than Ex due to design moment, then your Mx will change. Okay, your new Mx will be Ex minimum into P, right? Similarly in case of Ey also. Okay, so if your Ey minimum is found to be greater than Ey actual, then your design moment My will change, that will be equal to Ey minimum into P, right? E minimum is equal to effective length Le by 300. That is for non-rectangular and non-circular section shape, it is recommended that for any given plane, Ey minimum is equal to effective length Le by 300, but not less than 20 mm. Okay. Now, when the concrete is subjected to uniform compression, in case of concentrically loaded column, the ultimate strain is limited to 0.002 and the stress 0.447 FCK is uniformly distributed over the whole cross section. The above stress strain curve has no relevance when the concrete is under pure compression. Okay, so this is our design curve in case of structure, right? When the when the column is under pure compression, this has no relevance. Okay, in that case you will have a constant strain of 0.002, which is ultimate strain in case of pure under pure compression column. Okay, uh, and the stress is 0.447 FCK, uniformly distributed over the whole cross section, right? In case of concentrically loaded column, which is under pure compression, neutral axis will be at infinity. Okay, when your column is under pure compression, okay, that is in that case, the neutral axis will be at infinity distance. Okay, this is something very important. Okay, now design strength of actually loaded short column. Okay, so type of column, tied columns. Design formula suggested by IS 456-2000. So this is the formula given in the code. PU is equal to 0.4 FCK into AC plus 0.67 FY into ASC, right? PU is the actual load on the column, okay? Or you can say PU is the load carrying capacity of the given column section. Okay, FCK is a characteristic strength of concrete. AC is the area of concrete. Okay, in which we do not include the area of longitudinal steel. Okay, so AC can be found as gross section area AG minus ASC, right? That is area of compression steel. Fi is the characteristic strength of the compression reinforcement, and ASC is the area of the longitudinal reinforcement for the columns. Okay. Now for spiral columns, uh, clause 39.4, compression member with helical reinforcement. The strength of the compression member with helical reinforcement satisfying the requirement of 39.4.1 shall be taken as 1.05 times the strength of the similar member with lateral ties, right? These are members with lateral ties. This is a member with spiral, right? Such spiral columns, the strength can be increased by 5%. Okay, so this strength is increased by 5%. Okay, type of columns, tied columns. This is transverse reinforcement, right? Details again, transverse reinforcement. A diameter of the spacing of ties and spirals suggested by IS 456-2000. The diameter of the lateral ties is governed by the requirement of stiffness rather than the strength, and so it is independent of the grade of steel. Okay. Tie diameter. This is a tie, right? Okay. The tie diameter should be larger of these two. That is maximum diameter of the longitudinal bar by 4. Okay. So take the largest diameter of the longitudinal steel divided by 4, and other is 6 mm. Okay. So you have to take greater of these two. Tie spacing, this is spacing, right? Should be least of this, right? First is D. So D is the least lateral dimension of the column, that is this and this dimension. You have to take the least dimension, and 16 times the diameter of the minimum diameter of the longitudinal bar. Okay, so take the smallest diameter out of this into 16. Okay, and that's 300. So take the list of this 3, right? And that is what you have to at least, the spacing should not be greater than that, right? Okay, so in case of helical reinforcement, helical reinforcement provide very good confinement to the concrete in the core and enhances significantly the ductility of the column at the ultimate nodes. Tie diameter, the specifications are the same. Okay, pitch, so this is the pitch, right? Pitch should be less than least of these two, that's 75 mm, or core diameter by 6. So this is your core, right? And pitch should be greater of these two, 25 mm or 3 times the diameter of the tie. Okay, the end of the spiral should be anchored properly by providing 1.5 extra ton. Okay, so when you're ending the spiral, you should take a full ton of the spiral plus another half ton so that it is anchored properly. Okay, the minimum diameter to be used in the column, the minimum diameter of the bar to be used in column is 12 mm. The minimum number of bars required in a rectangular column are 4. The minimum number of bars required for a circular column are 6. The minimum percentage of longitudinal steel to be provided is 0.8 of the whole cross section. The maximum percentage of the longitudinal steel area allowed is 6%, but usually in practice it is taken as 4%. The minimum least dimension of the column should be kept is equal to 300 mm. The minimum clear cover and concrete grade of column depends upon the exposure condition. These tables are given in IS 456-2000. Okay, columns are designed with the theory of strong column and weak beam. All columns shall be at least designed for the minimum eccentricity for the following reasons: in order to account for various uncertainties such as lateral loads not considered in design, live load placement not considered in design, accidental lateral eccentricities load, eccentric loads, slenderness effect underestimated in design, right? Column is designed as short column if it is found to be short along all the planes. The formwork of the column can be removed after 24 hours. Curing of column is must for 7 days. Wet gunny bags can be used for curing. Hacking of column is completed within 24 hours of deshuttering of the formwork. The strength of the compression member with helical reinforcement satisfying the requirement of 39.4.1 shall be taken as 1.05 times the strength of similar member with lateral tie. This is what which we have already studied, right? It is found that the spiral columns, even after concrete cover spelling, uh, the concrete in the core still carry on to take more loads until the spiral reinforcement yields in tension. Okay, so let me explain you through figure. Okay, you can see this column, right? Even the concrete cover is spelled, but still the column uh, continues to take more load until this spiral reinforcement yields, right? That is why spiral reinforcement for spiral columns are assumed to take more load, that is than the actual tied columns, right? This is the reason. Okay, because spirals confine the concrete very beautifully. Okay, so let me come back to the topic. Okay, so this is the reason, right? Okay, as per clause 39.4.1, the ratio of volume the ratio of the volume of helical reinforcement to the volume of the core shall be greater than equal to 0.36 Ag divided by A core minus 1 FCK by Y. Okay, Ag is the area of core section, the area of the gross section. Sorry, it's the gross section. A core is the area of the core section, right? This is area of the core section, right? Fine. FCK is the characteristic strength of concrete, and Fy. Fy is the characteristic strength of the spiral, but not exceeding a value of 4.5 Newton per mm square. Okay. So this is what all which is to be covered in chapter 11. That is part 1 of this video. In part 2, we'll see the design of column. Okay. I hope you must have found this video useful. Thank you.